Okay, so back again. Hello, everyone. Last time we built we repurposed our language transformer code into a vision transformer and started training it. Now we're going to deploy it to run pod, scale it up. Um, I'd like to see the accuracy get to be about the validation accuracy get to be about 85%. So let's see what we need to do to get it to be that. These models, while like a data set like CIFAR-10 is relatively easy, like when you're building models from scratch, right? Like it's not necessarily that easy to get 85% accuracy, right? Like you do need to know what you're doing, and like so let's kind of like walk through the process of how we might get there. So like let's look at our code that we're gonna. It's already open. So yeah, I believe this is where we stopped last time. We download the CIFAR-10 data, and then we compose this data set when we get a batch. So we resize it to image size, which is 32. Actually, this is doing nothing because CIFAR-10 data is 32 by 32 pixels by default. Then we turn it to a tensor, and then we normalize it. We normalize. We transform the pixels into a standard normal distribution. We transform the pixels by a standard normal distribution. I modified a few things because what happens when I run this in run pod and then I create a screen in order to run it in the background. So essentially we want to create a screen, so we detach the process that we are using to train the model from the SSH process. That way, if I kill the terminal, the SSH connection, the training is still running on a separate process. There are different things you can use. I use Screen. I also use tmux, but Screen is just easy to use right now. I don't feel like setting up tmux. So maybe I'll do that in the future, actually. I probably will. For now, we're using Screen, but whenever I create a screen and then I run the code, the TQDM load guard is acting weird. So that prompted me to save the train, to just create logging, which is just what we want to be doing anyways, to track the losses. I'm not doing great logging. I need all of your training and validation iterations, all of your training should be logged very, very well with very specific folder names with your hyperparameters attached, and so you can very easily track your experiments. I'm not doing any of that well right now, so we're going to build that stuff up over time, and I'm going to show you how I do that. I'm basically going to just log all of my work, right? Document all of my work on YouTube. So, where was I? So what I did is I modified the code to log, and I just called it VIT write out. So my headphones plugged in. They are. pretty sure my audio is not coming from my headphones, so we should be good. It looks like OBS is showing it's from the mic. So I wanted to show you all this in steps. So just where I have the logging, I'm using a learning rate scheduler, but right now I just want to show you kind of the steps that I worked through on my own. Basically, from where we left off, I only added logging. So here I added this logging, and then it's essentially writing to a file in the same directory called traininglog.txt. And then I just copy and I just move the training logs successively to this directory. Which I will add much more utility and functionality to logging in the future so we can track things easily and automatically. So let's see. Okay. Code files just look better with numbers, with line numbers. Just going over this. So let's see if this runs here. My environment is active. So I got rid of the TQDM load bar. What I could do is have just separate environments and environment files that use TQDM when it's local and don't when it's deployed, or I don't know. There are a bunch of different ways we can do this, but just kind of want to get to the point. Maybe I should have decreased the number of. Okay, here you go. All right, so. Um, 3050, yeah, it appended it. Yeah, this is good. So this is where we are in RunPod. So let's run. Yeah, I don't know why. I guess it had nothing in it. Okay. So let's run. So first of all, let's create a screen. Let's see if I have any screen minus X or SVIT minus X quit. So that, let me delete, so that should delete that screen. So then I'll create a new screen, VIT, activate the environment. I'm in the same directory. Make sure I need to make environment files. This isn't gonna work. I need to make this cleaner just to show you all. I won't have to keep editing code on the server. It's not really the way we should be doing it. Oh, also I wanted to take these out. Those weren't there. It's really, you really shouldn't be doing things in screen. It just messes stuff up. Screen is really just to start a process and then detach from the screen and let it run in the background. So note to self: get tmux working for these videos, and also get environment files working, and also clean up logging and make it more automatic. So this shouldn't have a scheduler, it shouldn't update the scheduler. And this should have, does this have a learning rate parameter? Yes, 1E -3, that's what I had it at before. So okay. So let's see what happens when we run. Let's see what happens when we run this. Actually, I started with P dropout at 0.1. Yeah, let's see what happens when we run this. So minus R, we attach the VIT. Up, boom. Yep, looks about right. Yep, that's about right. Python, VIT, right. So should see it steadily start to climb up, and then I already know what's going to happen, but I want you all to see the process that I went through. Alright, so let's put that in the background, and then I'll pause the video, and then unpause it when training is done. So, training finished. I let training run for a while, for about 150 or something like that epics, and then I stored them in this log. So, back on my local machine. So, basically what we can see is that the model overfits. Right around here, things are still close. Training accuracy, or training loss, validation loss, train val accuracy, pretty close, and then it starts to, train accuracy starts to climb up, and validation accuracy stays the same, right? Basically, that's classic sign of overfitting. So, what I decided to do, one, first, just start with your basics. Also talk to GPT. Start with the basics, and then talk to GPT if your basics don't work. What are some things that could make this model overfit? Right, overfitting is basically you have too many parameters, and roughly speaking, a rough way of saying overfitting is you have your model is too complex for the data, and that could be that complexity could be in the sheer number of parameters. It could be in how the parameters are architected. It could be in the fact that you don't have enough regularization. It could be like your loss curve is too jagged. But generally speaking, your model is too complex, right? These are the parameters that we're looking at. Actually, let's kill this. Let's go to so this is on the server. So these are the parameters it ran with. Batch size 512. I think that's good. I think anything less than that might cause unstable training. You want your gradients to be averaged over a decent enough size batch such that the batch is representative of the data, and so you'll average out any anomalous behavior. Patch size, that's small enough. I mean, we could do 2, but 4 is pretty small. Relative to 32, I guess it's not that small. It's still small, I guess. It's small enough to be able to detect, to segment specific things within the image that could be classified within a patch, right? Number of embeddings, 256. I feel like that's reasonable for a patch vector of size 16 with 10 classes. Channels 3, heads 8. This all seems reasonable to me, just based on intuition. Dropout, that's a little low. That's the first thing that I identified actually as being a little low. Could even make it 0.3. We can just change the epics. We can make it higher just to let it run a little longer. Learning rate, this is the other thing. We want to, first, then kind of sort of going down the list of things that I was thinking to do was adding more, making the model more robust by adding data augmentation. So this can prevent overfitting because it sort of just flips the images. It augments the data to make the model more robust. So I added random horizontal flip, random rotation, random crop. There is also a default set that PyTorch provides, like, whatever the most optimized model is for the CIFAR-10 dataset. There are settings that store like those optimizations, and then they also store the data augmentations along with it. And you can use that, but I mean, it's good to just mess around with this stuff for yourself and use your own intuition and see where it goes. I mean, that's how you learn. The other thing I did is I used the learning rate scheduler. I'm going to use a learning rate scheduler. So that basically just decays the learning rate based on some kind of algorithm. I'm using cosine annealing. So it decays the learning rate as time moves on. So you start with a large learning rate, and then as your epics, each epic, your learning rate gets smaller and smaller. Um, this can help prevent overfitting. We want a learning rate scheduler can help with overfitting because like we can have the learning rate be larger in the beginning. That can help it escape suboptimal local minima that might lead to overfitting. But we don't want the learning rate to stay large because we want it to learn in a more fine-grained fashion, um, as you know, as the learnings become more as the learnings become more fine-grained, we want the learning rate to adjust to that, right? So we don't want to start by, we don't want to start by making massive leaps that jump over these local minima, but then keep making these massive leaps and miss the finer grained learnings, right? This stool is moving. It's pretty annoying. So, where am I? Okay. So let's uncomment the code for the scheduler. You can just take that out completely. We're not going to use that. So, all right. So we added more data augmentation. We added, um, we increased the number of epics a bit just to let it run a bit more. We added a learning rate scheduler, and we increased dropout from 0.1 to 0.2. I think I need a bit more dropout. Let's see. Yeah, let's see where this leads us. No screens. Did I change any other files? Right, of course, training log, but we can. All right. Let's just make sure it's running with no errors. The camera, yes I am. Okay, cool. So we'll detach from this, Control A, and then still holding Control, you hit D, that deattaches the screen. Yeah, and then we'll pause the video and come back. Well, so I already ran that, so I'm gonna just go back into this screen minus R VIT. We're gonna kill this. I'll save you the suspense. SVIT minus X quit, so we'll delete that screen. So what happened when we ran that? Where am I? Oh, yes, back to training logs. is things were looking great. We made it further than we did before. 20, 30, 40, 50. We hit it around Epic 66. Things were looking great. Training accuracy and val accuracy were still pretty close enough. And then, boom, Epic 66, train loss blew up. And then from that point forward, everything went wacky. Train accuracy went way down, started going way down after that, and it just kept happening. So that's a sign of exploding gradients. So we're going to try gradient clipping and see what happens. And I added some code for gradient clipping. So let's find the code for gradient clipping. Also, these are custom modules that I'm implementing, right? So there are a lot of things that these PyTorch default, Vision Transformer modules are doing. There are a ton of things that they're doing that I'm not doing. But this is all for learning and educational purposes, right? This is to increase our abilities as scientists, as machine learning engineers, like we want to really know how to manipulate these neural networks and these architectures at a very foundational level so we can have a lot of power. This is all about power, guys. Power is great. If you don't like power, don't tune into this channel because I'm all about power in all aspects of my life. Like, I love power, and not power that you can use to wield over others, but power that you can use to make yourself and other people more powerful around you, the people more powerful around you. So I love power. Love me some power. So, okay. Yeah. This is what I added. Now I wanted to add this. So with this, we can log the gradient norms, periodic. I already deleted this. So yeah, we're gonna, basically we're gonna take the norm of the gradients, and if it goes above 1, we're gonna clip it. We're gonna keep it bound underneath 1. All right. We're gonna see. Actually, we don't even need to log these now. Well, yeah, who cares? We don't need to log this now. Make sure I didn't make any other crazy changes. Oh. Yeah, see. Okay. gotta add in all the other stuff I did. I shouldn't have modified anything on the server. That was my fault. Oh, I do have it there. 0.2 for dropout. I do have, yeah, scheduler. Gradient clipping, dropout, num epics, augmentation. Learning rate. This looks good. Okay. All right. Let's make sure this runs for training and the validation epic, and then we'll pause the video. All right. So let's see what happens this time around. So let's check out the losses. Actually, we can see them here. Looks like it's the numerical instability and exploding gradients problem around Epic 66 has gone away, but it still looks like it's overfitting. The training accuracy is increasing, and the validation accuracy is staying around 75 or 77%. I don't think that's going to change. So let's stop the training. So I think, our vision transformer works. The architecture, it works. The thing is, vision transformers are data hungry. They're they're complex models. That means they have a lot of parameters. The self-attention mechanism in and of itself is a parameter heavy operation. And then when you start increasing the number of heads, increasing the number of transformer blocks, increasing the embedding size, these models can overfit pretty easily. So I would like to continue this investigation of how to get our vision transformer to be at 85% accuracy or higher on the CIFAR-10 data set. But my curiosity right now is kind of moving in a different direction. I want to try um, a model with that is a bit less data hungry and but does have inductive bias. So that means it does make the model does make certain assumptions about the the way that about the tensors, about the input data, because it does use convolutions. So it is expecting there is a certain ordering that is inherent to um, the architecture of a model that uses convolutions, and it does have inductive bias, um, which isn't a bad or a good thing. It just is what it is. And this is compared to a vision transformer, but I do think that ResNet. My intuition says ResNet should be pretty easier. We should be able to more easily fit ResNet, or get like 85% and above accuracy using ResNet 18 on the CIFAR-10 data. So I'm gonna stop this video here, and the next video is we'll be implementing the foundational modules for ResNet um, in PyTorch. Again, I don't have my iPad. Once I get my visa here in Thailand, I'll leave the country, go home, get my capture card so I can use my iPad. Because ideally, what I would do is I would draw Resonant 18. I would draw everything. I would draw the convolutional operations, make it very clear what's happening, and then I would implement it in PyTorch. You'd be very clear what the different unfold operations are doing, what the views are doing, what the matrix multiplication is happening. Like, why are convolutions just simply sliding dot product operators? Why are they called feature maps? Um, how does batch normalization differ from layer normalization? These things, like, when you draw them out and when you implement them, you get a very good feel for how these models work. So but I do want to work. I'm hungry to just start work. I'm eager to work. So I'm going to implement Resonant 18 in the next video. That means I'm going to implement convolution, convolution using PyTorch Unfold, convolution 2D. I'm going to implement max pool 2D, average pool 2D, max pool, average pool, convolutions, batch norm 2D, and that should be all the foundational modules for Resonant, and then I can start making Resonant blocks um, that use convolutions, ReLU, convolution, batch norm, ReLU, um, and then convolution, batch norm, ReLU, and then a skip connection that possibly needs to downsample to match the output from the um, primary operation, concatenate, and then add it, add the identity to the computation. And then we stack those blocks. Basically, we just stack those blocks, and each block extracts um, feature maps of higher orders of increasing level of complexity. Um, and yeah, and then we'll run the CIFAR-10 data through. First, we'll test it on MNIST just to make sure it works. Then we'll run the CIFAR-10 data through it and see if it's easier to get. My intuition is that it's going to be easier to get um, better accuracy, better validation accuracy out of Resonant 18 more quickly than it would be a Vision Transformer. Um, Yeah, and then we're gonna talk about inductive bias, and then we're gonna kind of compare Resonant 18 division transformer and see what we can learn by the juxtaposition of the two. Um, I think that sounds cool. That's interesting to me. So yeah, and then I think after that we're gonna start moving towards our diffusion model. So and then take small detours along the way. You know, I'm gonna have to implement a variational autoencoder for the diffusion model in UNet. Um, and then for some diffusion model improvements, I might need to implement a generative adversarial network for distillation. I think, yeah, we got some fun stuff coming along. So, yeah, thanks for tuning in. Later.